Welcome back, guys. It's Britter back with the Odin Project, and we're still in Foundations, but we have moved on to Git Basics. And so we're going to jump into the introduction to Git. Git is like a really epic save button for your files and directories. Officially, Git is a version control system. A save in a text editor records all of the words on a document as a single file. You are only ever given one record of the file, such as sa.doc, unless you make duplicate copies, which is difficult to remember to do and keep track of. However, a save in Git records differences in the files and folders, and keeps a historical record of each save. This feature is a game changer. As an individual developer, Git enables you to review how your project grows and to easily look at or restore file states from the past. Once connected to a network, Git allows you to push your project to GitHub or other alternatives such as Bitbucket, Beanstalk, or GitLab for sharing and collaborating with other developers. Please note, we only support GitHub within our curriculum and will not help troubleshoot the alternatives. While Git works on your local machine, GitHub is a remote storage facility on the web for all your code and projects. This means that by learning Git, you will get to showcase your portfolio on GitHub. This is really important because almost all software development companies consider using Git to be an essential skill for modern web developers. Having a GitHub portfolio will provide proof to future potential employers as to what you are capable of. In this lesson, we will briefly explore the history of Git, what it is, and what it's useful for. In the next lesson, we will go over the basic workflow for using Git, which should enhance your understanding and demonstrate why Git is so useful. Finally, you will set up a project with Git that will serve as a template for your future projects. For now, let's learn what Git is and why it's so powerful. This section contains a general overview of topics that you will learn in this lesson. Explain what Git and GitHub are and the differences between the two. Describe the differences between Git and a text editor in terms of what they save and their record keeping. Describe why Git is useful for an individual developer and a team of developers. And so it says read chapter 1.1 through 1.4 in this book about version control to learn the difference between local, centralized, and distributed version control systems. Watch this video about how Git can improve the workflow of both an individual and a team of developers. It has several videos here, which we're not going to watch here, but I suggest you guys watch them on your own. If you haven't yet installed Git, visit Setting Up Git lesson, which we already did. Take a look at the Odin Project's very own GitHub repository. This is where all the lessons are stored. While you're there, look at all our contributors to gain an appreciation for how Git records all collaborative efforts and how GitHub visually represents this. Alright, so 1.1 through 1.4. Alright, so this chapter will be about getting started with Git. We will begin by explaining some background on version control tools, then move on to how to get Git running on your system, and finally how to get it set up to start working with. At the end of this chapter, you should understand why Git is around, why you should use it, and why you should be all set up to do so. About version control. What is version control and why should you care? Version control is a system that records changes to a file or a set of files over time so that you can recall specific versions later. For the examples in this book, you will use software source code as the files being version controlled through, though in reality you can do this with nearly any type of file on a computer. If you are a graphic or web designer and want to keep every version of an image or layout, which you would most certainly want to, a version control system, VCS, is a very wise thing to use. It allows you to revert selected files back to a previous state, revert the entire project back to a previous state, compare changes over time, see who last modified something that might be causing a problem, who introduced an issue, and when, and more. Using a VCS also generally means that if you screw things up or lose files, you can easily recover. In addition, you get all this for very little overhead. Local version control systems. Many people's version control method of choice is to copy files into another directory, perhaps a timestamp directory if they're clever. This approach is very common because it is so simple, but is also incredibly error-prone. It is easy to forget which directory you're in and accidentally write to the wrong file or copy over files you don't mean to. To deal with this issue, programmers long ago developed local VCSs that had a simple database that kept all the changes to files under revision control. Figure 1. Local version control. One of the most popular VCS tools was a system called RCS, which is still distributed with many computers today. RCS works by keeping patch sets, that is, the differences between files in a special format on disk. It can then recreate what any file looked like at any point in time by adding up all the patches. Centralized version control systems. The next major issue that people encounter is that they need to collaborate with developers on other systems. To deal with this problem, centralized version control systems were developed. These systems, such as CVS, Subversion, and Perforce, have a single server that contains all the version files and a number of clients that check out files from that central place. For many years, this has been the standard for version control. This setup offers many advantages, especially over local VCSs. For example, everyone knows to a certain degree what everyone else on the project is doing. Administrators have fine-grained control over who can do what, and it's far easier to administer a CVCS than it is to deal with local databases on every client. However, this setup also has some serious downsides. The most obvious is the single point of failure that the centralized server represents. If that server goes down for an hour, then during that hour nobody can collaborate at all or save version changes to anything they're working on. If the hard disk the central database is on becomes corrupted and proper backups haven't been kept, you lose absolutely everything. The entire history of the project, except whatever single snapshots people happen to have on their local machines. Local VCS suffer from the same problem. Whenever you have the entire history of the project in a single place, you risk losing everything. Distributed version control systems. This is where distributed version control systems step in. In a DVCS, such as Git, Mercurial, Bazaar, or Darks, clients don't just check out the latest snapshot of the files. Rather, they fully mirror the repository, including its full history. Thus, if any server dies and these systems were collaborating via that server, any of the client repositories can be copied back up to the server to restore it. Every clone is really a full backup of all the data. Smart, smart, smart. Distributed version control. Furthermore, many of these systems deal pretty well with having several remote repositories they can work with, so you can collaborate with different groups of people in different ways simultaneously within the same project. This allows you to set up several types of workflows that aren't possible in centralized systems, such as hierarchical models. Getting started. A short history of Git. As with many great things in life, Git began with a bit of creative destruction and fiery controversy. The Linux kernel is an open source software project of fairly large scope. During the early years of Linux kernel maintenance, 1991 to 2002, changes to the software were passed around as patches and archive files. In 2002, the Linux kernel project began using a proprietary DVCS called BitKeeper. In 2005, the relationship between the community that developed the Linux kernel and the commercial company that developed BitKeeper broke down, and the tool's free-of-charge status was revoked. This prompted the Linux development community, and in particular Linus Torvalds, the creator of Linux, to develop their own tool based on some of the lessons they learned while using BitKeeper. Some of the goals of the new system were as follows: speed, simple design, strong support for nonlinear development, thousands of parallel branches, fully distributed, able to handle large projects like the Linux kernel efficiently, speed, and data size. Since its birth in 2005, Git has evolved and matured to be easy to use and yet retain these initial qualities. It's amazingly fast, it's very efficient with large projects, and it has an incredible branching system for nonlinear development. Getting started. What is Git? So what is Git in a nutshell? This is an important section to absorb because if you understand what Git is and the fundamentals of how it works, then using Git effectively will probably be much easier for you. As you learn Git, try to clear your mind of the things you may know about other VCSSs, such as CVS, Subversion of Perforce. Doing so will help you avoid subtle confusion when using the tool. Even though Git's user interface is fairly similar to these other VCSs, Git stores and thinks about information in a very different way, and understanding these differences will help you avoid becoming confused while using it. Snapshots, not differences. The major difference between Git and any other VCS is the way Git thinks about its data. Conceptually, most other systems store information as a list of file-based changes. These other systems CVS, Subversion, Perforce, Bazaar, and so on think of the information they store as a set of files and the changes made to each file over time. This is commonly described as delta-based version control. Storing data as changes to a base version of each file. Git doesn't think of or store its data this way. Instead, Git thinks of its data more like a series of snapshots of a miniature file system. With Git, every time you commit or save the state of your project, Git basically takes a picture of what all your files look like at that moment and stores a reference to that snapshot. To be efficient, if files have not changed, Git doesn't store the file again, just a link to the previous identical file it has already stored. Git thinks about its data more like a stream of snapshots. Storing data as snapshots of the project over time. This is an important distinction between Git and nearly all other VCSs. It makes Git reconsider almost every aspect of version control that most other systems copied from the previous generation. This makes Git more like a mini file system with some incredibly powerful tools built on top of it, rather than simply a VCS. We'll explore some of the benefits you gain by thinking of your data this way when we cover Git branching and Git branching. Nearly every operation is local. Most operations in Git need only local files and resources to operate. Generally, no information is needed from another computer on your network. If you're used to CVCS, where most operations have that network latency overhead, this aspect of Git will make you think that the gods of speed have blessed Git with unworldly powers. Because you have the entire history of the project right there on your local disk, most operations seem almost instantaneous. For example, to browse the history of the project, Git doesn't need to go out to the server to get the history and display it for you. It simply reads it directly from your local database. This means you see the project history almost instantly. If you want to see the changes introduced between the current version of a file and the file a month ago, Git can look up the file a month ago and do a local difference calculation, instead of having to either ask a remote server to do it or pull an older version of the file from the remote server to do it locally. This also means that there is very little you can't do if you're offline or off VPN. If you get on an airplane or a train and want to do a little work, you can commit happily to your local copy, remember, until you get to a network connection to upload. If you go home and can't get your VPN client working properly, you can still work. And many other systems, doing so is either impossible or painful. In Perforce, for example, you can't do much when you aren't connected to the server. In Subversion and CVS, you can edit files, but you can't commit changes to your database because your database is offline. This may not seem like a huge deal, but you may be surprised what a big difference it can make. Git has integrity. Everything in Git is checksummed before it is stored and is then referred to by that checksum. This means it's impossible to change the contents of any file or directory without Git knowing about it. This functionality is built into Git at the lowest levels and is integral to its philosophy. You can't lose information in transit or get file corruption without Git being able to detect it. The mechanism that Git uses for this checksumming is called an SHA-1 hash. This is a 40-character string composed of hexadecimal characters 0 through 9 and A through F, and calculated based on the contents of a file or directory structure in Git. A SHA-1 hash looks something like this. You will see these hash values all over the place in Git because it uses them so much. In fact, Git stores everything in its database not by file name but by the hash value of its contents. Git generally only adds data. When you do actions in Git, nearly all of them only add data to their Git database. It is hard to get the system to do anything that is not undoable or to make it erase data in any way. As with any VCS, you can lose or mess up changes you haven't committed yet, but after you commit a snapshot into Git, it is very difficult to lose, especially if you regularly push your database to another repository. This makes using Git a joy because we know we can experiment without the danger of severely screwing things up. For a more in-depth look at how Git stores its data and how you can recover data that seems lost, see Undoing Things. The 3 states. Pay attention now. Here's the main thing to remember about Git. If you want the rest of your learning process to go smoothly, Git has 3 main states that your file can reside in: modified, staged, and committed. Modified means that you have changed the file but have not committed it to your database yet. Stage means that you have marked a modified file in its current version to go into your next commit snapshot. Committed means that the data is safely stored in your local database. This leads us to the three main sections of a Git project: the working tree, the staging area, and the Git directory. Working tree, staging area, and Git directory. The working tree is a single checkout of one version of the project. These files are pulled out of the compressed database in the Git directory and placed on disk for you to use or modify. The staging area is a file, generally constrained in your Git directory, that stores information about what will go into your next commit. Its technical name in Git parlance is the index, but the phrase staging area works just as well. The Git directory where Git stores the metadata and object database for your project. This is the most important part of Git, and it is what is copied when you clone a repository from another computer. The basic Git workflow goes something like this. You modify files in your working tree. You selectively stage just those changes you want to be a part of your next commit, which adds only those changes to the staging area. You do a commit, which takes the files as they are in the staging area and stores that snapshot permanently to your Git directory. If a particular version of a file is in the Git directory, it's considered committed. If it has been modified and was added to the staging area, it is staged. And if it was changed since it was checked out but has not been staged, it is modified. In Git Basics, you'll learn more about these states and how you can either take advantage of them or skip the stage part entirely. And so we've got to read 1.4. Getting started, the command line. There are a lot of different ways to use Git. There are the original command line tools, and there are many graphical user interfaces of varying capabilities. For this book, all we will be using Git on the command line. For one, the command line is the only place you can run all Git commands. Most of the GUIs implement only a partial subset of Git functionality for simplicity. If you know how to run the command line version, you can probably also figure out how to run the GUI version, while the opposite is not necessarily true. Also, while your choice of graphical client is a matter of personal taste, all users will have the command line tools installed and available. So we will expect you to know how to open terminal in Mac OS or Command Prompt or PowerShell in Windows. If you don't know what we're talking about here, you may need to stop and research that quickly so that you can follow the rest of the examples and descriptions in this book. Alright, and so Odin Project only told us to read through 1.4, so that's what we're going to do. And let's go ahead and take a peek at the GitHub repository for the Odin project. And there are 59,267 commits. And I don't particularly know exactly what we're looking at yet, but I have a feeling that we are soon going to find out how all this works. Alright guys, I am going to go ahead and mark this complete. You guys are more than welcome to check out these additional resources, and I do advise you watch the videos above, and I'll see you on the next one.